Okay, good evening to all of you. So we will discuss the fourth part, no, of our topic for today. So the topic is more on instrument transformers. So the instrument transformers here is designed for our current transformers, which is a vital part on the design of your current transformer or CT transformer in your relays. If you can still recall that the relays has CTs, and every current transformer there in terms of the design has a burden. So you need to multiply it by a certain ratio factor or the effective turns ratio so that you can get the actual CTR of your current transformer. But instrument transformers are divided into two types. It can be a voltage transformer or a current transformer. So we will make use of the current transformer instead because the voltage transformers are more on the metering side, while the current transformer, which is our main goal, is for the overcurrent side or on the protection of faults or in terms of faults. So we will make use of the CTs instead of the VTs. So we will concentrate on that on this slides. Okay, let us have the introduction of your current transformer, your instrument transformer rather. Your instrument transformer are also called transducers. We already described transducers last time. From what is a relay all about? Okay, the transducers here, okay, are of course the main function is to give you a lower value of your quantity or your voltage or your current quantity. That's the main goal. If you have a transducer, you convert this higher voltage or higher current to a lower value. That's the main goal. It's not that's the main reason for transducers, right? So that if you need 5 amperes or 100 amperes at the secondary side, it can be done by this transformer. So the primary function, no, of your instrument transformer is to provide values or lower values of your voltage and current in terms of magnitude, of course, and it will also provide galvanic isolation, meaning you isolate the power network to the relays and other instruments to the transducer secondary winding. Kaya siya magiging isolated, right? So you have an isolated value simply because of the presence of your transformers. And these transformers, of course, converts these values to a lower magnitude. In the US, current transformers, which is our main, the secondary windings is on 5 amperes. Or in Europe, and the standard is 1 ampere. Please take note of this. Why? Because if you see current transformer table, especially multiple ratios, you can see 100 by 5 and then sometimes it's 20 by 1. As you see, the ratio 100 by 5 and 20 by 1 is definitely 20, right? But if you can see here, this is an IEEE standard and this is an IAC standard. They are the same. So it depends on what country that you design in your system. But in our goal here, we use IEEE, right? Because the frequency 60 in the Philippines, we also use frequency 60. So we use the IEEE standard. But again, how you design the system is also the same, okay, with the same methodology or the same procedure, okay? So in this case, if the secondary winding is in 5, you have an IEEE, and if your secondary current rather on your CT ratio is 20 by 1, you're considering a European standard. Okay. Now, let us move forward to the voltage transformers. Well, on voltage transformers, the secondary windings are rated 120 volt. And if you divide it by square root of 3, the answer is 69.3. Now, in current transformers, it need to withstand at least 50 times the full load current. So you know the full load current is our base current. So it's dependent on what is the rating of your transformer in MVA and divided by the specific voltage referred to primary or secondary. Okay, while the VT requires an overvoltage of 20% normal value. So if you have a voltage transformer, you have a current transformer, you have those threshold values so that it will not be overheated or sometimes oxidized because of over current and over voltage. Okay, these are your instrument transformers. It has three types. Okay, paano malalaman yung three types? Una, wound primary type. So the wound primary type is like this. Okay, this is the wound primary type. And then your bar type is like this. And this is the familiar on our laboratory, no? The bushing type, or there's a hole, okay, on the your core, right? So this is a window type, a bar type, and a wound primary type. Okay, we can move forward. Okay, now your instrument transformer, voltage transformer, you have two types. It can be a magnetic type or a capacitor type. So this is the magnetic type and this is the capacitor type. Well, we will not go to details of this because our main goal is current transformer. But we just give you a brief introduction on how they are classified into types and classifications. Okay, moving forward. Okay, let us move forward to the technical part, at least for a meantime. Okay, so your current transformers is like, if you can still recall your transformers, if you refer to the primary and the secondary side. Okay, if you have this, this is the equivalent circuit of your current transformer. Okay, it is always 1 all over n, no, the transformation. Okay, in terms of the transformation of your, okay, say transformation A of your or current transformer is 1 by n, because your main goal always is if you have a higher current, it must be lowered in a certain value. That's why it's called a transducer. For example, you have a 5,000 amperes. Okay, and 5,000 ampere, you have a 600 by 5. Okay, current transformer ratio, or I could say your A, or simply the words that is 1 over n, definitely. So I want my secondary winding. So instead of multiplying it by A, it is 1 all over A, or 1 over n. Because simply, if you divide the 600 by 5 here, okay, by the 5,000, it will lower to a certain value. So if you multiply it by A, definitely what happens will increase the value, right? So instead, you divide it by the N or A. Okay, N, A, you already know A is the transformation ratio. The N here is also your A. Okay, so this is the whole circuit, and we transform it with respect, okay, to the secondary sides of the transformer. So for this, you can still recall, okay, some of the transformation ratios, right? So A squared is simply equal to what? No, Z1 all over Z2, right? So another transformation ratio is in terms of your secondary I2 over I1, if you can still recall, which is equal to V primary is secondary. But this is different when it comes to, okay, current transformation ratio, because your A here is 1 all over N now. Get IS, okay, IP over A. Okay, so you can see it on the next few slides. Okay, that in this case that you want to transform, okay, your parameters here. Please take note, no, your A now is equal to, no, 1 all over N. Okay, I can erase this part here so that you will not be confused. My first. letter here is, yes, this is your A. It's different. Okay. So the N is your transformation ratio. Okay, now let us move forward, no, to the next slide. Okay, we clear all the drawings, so you can go back to that slide if you miss some things. Okay, before we proceed there, okay, please take note the following. The primes here are the secondary, your secondary winding. Your prime here is the secondary winding. So our main goal is, okay, you need to convert. You can still recall your basic transformers that you can convert your transformer with respect to primary and secondary side. So please take note that that in this type of sequence that you need to transform your equivalent circuit in the primary to its in secondary side, and taking note that your transformation ratio is inverse in this kind of situation, simply because the current transformer is dependent on the variables of the secondary side with the lower value. Okay, in this case, we can now move forward here that the I prime here is the secondary. Okay, this is I1 prime. Then Zm prime here, okay, here is converted to the secondary part of the transformer. So dito yung sinabi natin na you divide it by A, right? So to get I1 it turns to secondary. And this one, okay, that is in terms of the secondary by Zt all over Zn, right? So we convert the primary to the secondary side. Okay, now we have this values now, okay, on your secondary side of your transformer. Okay, this one and this one. Okay, we already converted to the secondary side. Considering again, no, that your ordinary A is now equal to 1 over N. And please take note that the N is the transformation ratio for, okay, your current transformers. That's 1 all over N. That's the only difference. Okay, without further ado, we can now go to this phasor diagram. So using this phasor diagram, considering EB, okay, as our reference, please take note, this is your leakage impedance ZX2. Sometimes, this leakage impedance is approximately zero. It is sometimes, okay? But if ZX2 is given, then you must include that, no, on the model of your current transformer. So you have your B and then your I2 here, okay? So considering lagging, yes, okay? So I2, okay, will lags EB by a certain angle. I could say theta here. And then, okay, we can eliminate that. If you have ZX2 here, okay, it will have like this, ano? So, but it does not have any real part. Because if there's a real part there, so 90 degree ito, and then this is the total. However, there's no real part. So therefore, your ZX2 now is also your impedance. Okay, total. Kasi your ZZ here must be ZR plus ZX in terms of polar representation or vector representation. But ZR is 0. So that's whatever your impedance, okay, it is also your reactive value because only reactive value is present. Okay, that is your, this is your vector here. By adding, okay, your EB by ZX2, it will become EM. And it has an angle, for example, alpha. Okay? And definitely, whatever your EM here is also the secondary side voltage of your transformer because they're connected parallel. However, the currents will be different because the current I1 will be dependent on whatever your current at the magnetizing uh, coil of your transformer plus I2. So this is your I2 here. So if you add I2 and IM, definitely it will yield with I1. So there's an I2 here. Okay. So I could say it is lagging condition and it has a skew a little bit because as you can see, this total impedance, it can be R plus JX, right? It's not a straight line downward like this, which is lagging by 90. Okay, now in this case, I could say it has a skew like this. And then I2 plus IM is definitely equal to the vector of I1. Thus, you can have this vector diagram of this, okay, of this equivalent circuit. Okay. Okay. Now we can now consider the following. So this is the conversion factor from with respect to the secondary side, and then definitely you can get EM by EB. Okay, you have your EB here definitely, plus the drop I to ZX2. But if ZX2 is zero, EM is EB. Okay. And then the magnetizing current is dependent on E2, EM all over ZM, but EM can be also your secondary voltage simply because if this is the terminal no, of the secondary side of the transformer, that is also equal to the magnetizing voltage at this portion here. Okay. Now we can now clear all drawings, then move forward. No? Okay, your current transformer, as I have mentioned, the primary current is I1 is equal to plus IM. Now, definitely, we have the transformation per unit current transformation ratio error. So, per unit current transformation error is defined by this formula here, which is the difference between I1 and I2 by all over I1. But here you can get I2, IM rather, by having the difference of I1 minus I2, current difference. So therefore, it is IM over I1 as well. Okay. Then more often that the CT error is presented no, in terms of the correction factor R. So this correction factor R, kaya nga siya sinabing correction factor, unitless unit. Unitless. Of course, because if this is amperes and this is amperes, it will cancel out. And hence that error is in per unit. If you get the correction factor, this will be the factor that you need to multiply okay on the turns ratio so that you can get no the approximate current transformer ratio with burden involved or error involved. Okay, sometimes it is used, but on majority of some of the calculation to become it automatic, no, your R is definitely equal to 1. So if that is definitely equal to 1, it means no error. But there are some, okay, some instances that this R must be multiplied because there are some burdens, okay, that is has an effect on the overall CTR ratio. So we'll discuss the burden on the next few slides. So as you can see here, the ratio correction factor R is defined as a constant by which the nameplate turns ratio of N of a current transformer must be multiplied to, okay, get the effective turns ratio. So the effective turns ratio is you already multiplied the error or this ratio by correction factor error. So if you multiply R by the current transformer ratio, you can get the effective turns ratio. So if you can still recall also your transformer, it has also the same thing. You can the drawings, so we will make use of this, no, or as an example in the next few slides here. Okay, we have this example. Okay, if we consider a current transformer, it has a turns ratio of 500 by 5. So the 5 there is an IEEE standard because 5 amperes is on the secondary side. Now the secondary leakage impedance is 0.01 plus J.1 and there is a burden of 2. Okay, this burden, we can go back here. Okay, so this is the burden, the leakage impedance, and the magnetizing impedance. Please take note that this burden, what is this burden, sir? This is the actual model of the auxiliary of the substations. So what is this auxiliaries? It is your meters, the values of meters, your relays, for example, protective devices, etc. Okay, it is modeled in impedance, which is the so-called burden. So it means you already know what is a substation, right? That is your transformer. And then the front of transformer secondary, which is this is your transformer substation. Siyempre, there is some loads that is connected at the secondary side, which is definitely, it is considered as this parameters, your meters, your relays, and other devices. Kaya nga siya model of auxiliaries of the substation. Okay, please take note that we will make use of this diagram on the computation of problem on the other problems that we have. Okay, now we need to get the primary current referred to the secondary side in terms of I1 and the effective turns ratio. Okay, I will go back here. I just copy paste this one on the solution so that we can see definitely what we are solving here. Okay, now definitely it will explain this value. You can see here, how can we solve EM? Okay, we can solve EM here, okay, by having whatever the current, no, that is flowing here, which is IM, okay, multiplied by Zn. But however, as I have mentioned as well, if you already got the E2, the total voltage at the secondary side, this is also equal to EM. Okay, by analysis, how can you get E2? If you already got I1 and the total impedance up to the secondary side of the transformer, I could say ZT. However, how can you get ZT? It's pretty clear on the diagram. Given ZX2, given ZB, and given Zn, it's pretty clear, okay, that ZX2 plus ZB is in parallel with what? Zm. So this is called parallel. So when you say parallel, okay, sorry for this. Okay, when you say parallel, okay, it means, okay, that that's a product all over the sum, right? So as you can see, as we go back here, okay, this is the burden ZB. Okay, this is the magnetizing impedance ZX2, and this is the leakage impedance ZX2, and this is your magnetizing ZM. So product, okay, as you can see, all over the sum of the two. Uh, a little bit of circuitry. Okay, so for this, we can now solve the problem in terms of I1. Okay, so the I1 here is 1.92 bar 9.62 degree. Okay, now this in terms of I1 because the problem is in terms of I1. Okay, let us move forward. Now, this is your EM, which is equal to your E2. How can you get IM? Okay, now, as you can see here, okay, we can use also Ohm's law, right? So, to get IM, that is equal to E2, you divide it by whatever your magnetizing impedance ZM, which is 4 plus J15. So, this is your I1, and then this is your, definitely, your ZM. Okay, having the numerical value in terms of I1, we have this value here. Okay, this is in terms of I1 because at the end of the day, you can you can cancel I1 to get the error. This is what we have discussed no, from our previous slide, that you can get the error by having what? IM over I1. So definitely I1 will cancel out. Okay, and leaving behind, okay, 0.12 kasi IM is I1 times this value, right? If you divide by I1 will cancel out. So hence the answer is this. 0.1238 for negative 16.45. But this is not the final answer. We need the final answer in terms of the effective turns ratio based on the value of R, which is the error rate. Okay, so okay, in this way, we can now move forward to this, and then we can clear all the drawings here. Okay, the turns ratio, if you can still recall, okay, your R is 1 minus error E. Okay, if you go back, few slides back, okay, the R, that is the ratio correction factor that you need to multiply by the your CTR to get the effective turns ratio. Okay, but your E is just no the error, no error E, which is this one, okay, the transformation error, okay, that we use. So in this way, if you do this, okay, the answer, okay, will give us 1.468. As you can see, this is our main goal, to get this value here, not the bar angle, this value only. That you need to multiply to your turns ratio. Okay. However, this is for a burden of 2 ohms. Resistive to resistive. Okay, now, your burden is not resistive. You use reactive or you use resistive component or lower value of your resistive component. Because when you say ZB is 2 ohms, definitely this is purely resistive. But if you have a J already, you're considering your burden is inductive. Okay, you can see here that if I use ZB as 1 ohm, what happened? That your R is proportional to the burden impedance, right? So RB is the burden resistance. If you lower the burden resistance, you will have a lower, okay, ratio of error. Okay, so as you can see here, 1.025 versus 1.04. However, if for example my burden impedance is not real, we use a reactive component. So what will happen is, you can see here, it increases the burden. So it means definitely that if you want to have an effective turns ratio, that R, okay, which is your ratio of error, okay, must be, the burden impedance must be in resistive component, it must be lower in order to have the error, okay, lower as well. Because the error depends on the magnitude of the burden impedance. So this, the R here there is the effective turns uh, or the ratio of the turns, okay, error. So the higher of that, the higher the error, right? So the lower the impedance or resistive in term, the lower the error. Okay, now that's the moral lesson of the story. This one, okay, this uh, proportionality there or that relationship. Okay, now we can clear all drawings, then move forward. Okay, now you can also design no, the typical CT ratio by having curves like this. So it is also the same thing on how you model a DC machine, right? You can still recall your DC machines. There are some curves there that you will use. And then you can now get the secondary voltage versus the current, and then you can get the impedance, right? So here's the same thing, but instead, it dependent on the curve, C ratio, no, of the transformer. And this is so-called the magnetizing characteristic of a CT curve, okay? Because you know, already know, this is dynamic. The transformer has a dynamic response. What we have described, no, from the first example, you're considering a relationship linearly. But here it does not have. It has these curves, okay, knee curves. So if you want to use these knee curves, so this is the true value, no, of your CT ratio, and we can make use of this as an example. Okay, we can have this as the nonlinear performance of your transformer, because Am now is not constant, and the actual excitation characteristic of the transformer must be taken into account in determining the factor R for a given situation. Okay, please take note that your current transformers has different ratios. It is called a multi-ratio. Okay, so this the complete multi-ratios. It can be high as up to 3,000 by 5. Okay, let us have this example, and we will make use of that curve later. Okay, consider a CT with a turns ratio of 600 by 5, and the magnetizing characteristic corresponds to this ratio in figure 0.4.3, which is the knee curves. It is required to calculate the current in its secondary side for a primary current of 5,000 ampere. If the total burden is 9 plus J2, this is the burden on the load, and the secondary leakage impedance is negligible. So Zx will be almost zero because negligible. Excuse me. The impedance angle of the magnetizing branch is bar 60, okay, or 60 degree. So you do not know the magnitude of your Zm, but you will have the bar angle 60 degree on the Zm. So how can you solve this problem? So it is explained in the next few steps. Okay, first, since the magnetizing branch is not is nonlinear, so it means the value of Zm. We may consider the equivalent circuit made of a linear part, no, considering the current source must be uh, in the secondary side. So your 5,000 there, instead of multiplying 600 by 5, no, you need to divide it by 600 by 5. As you can see here, it's pretty clear. Okay, so your 5,000, okay, you need to divide it by, okay, 600 by 5 in order to have the value of the fault current, okay, into the secondary side in a lower value. The answer here is 41.67 amperes approximate. Okay, that's correct. Okay, so you do not need to have the current in a higher value because, you know, current transformers are transducers. So you need to have a lower value, of course. Now, it is in parallel with the burden. If we can still recall, okay, so if we go back here on what we have described, no, on the equivalent diagram, so we will make use of that definitely in this example. Okay, okay, sorry for that. Okay, this is your ZB. Okay, now as you can hear, no, we can eliminate ZX2 now. It will become zero. Why? Because there's no value. Now, if there's no value here, definitely whatever your EB here is equal to your EM, right? By analysis. Okay, now it can simplify things up. Okay, now also in parallel with the burden, now there's an across, no, that you have your ZM, of course. They are not parallel now. As you can see, nakaparallel na sila, right? Because there's no X2. Now, the Thevenin equivalent, you can already compute for that, di ba? By transformation ratio. You have 41.67 in parallel with this burden impedance. because they are connected in parallel right now, right? So, it is like transformation ratio. That IN is equal to Thevenin's voltage, you divide it by whatever your ZTH is. So to get VH, multiply IN by ZTH. Now your IN is 41.66 multiplied by 9 plus J2. The answer is 384.1. There's a value there. If I'm not mistaken, the value of that is 12.53. No, definitely. Okay. The value of this, you have a value of 12.53. But we will make use of this value as reference. And then we will, okay, uh, go back to that value later. So we will make use this as reference because it is nonlinear. So we will make use of that on the next few slides to get the value of IM later. So we will make use that as our reference. So instead, 12.53 no, will be equal to bar zero for now so that we can get the value of the other parameters, which is your IM. Okay, so this is 384 in the magnitude part, and we make use of that as our reference as bar zero. Then we will make use of the 12.53. Okay, we will turn it back when we go to the analysis part of your magnetizing current. Okay, we can clear all the drawings here. Okay, we will make use of that diagram later. Okay, now it will become like this. Okay, going back this one on this diagram. Okay, now from the circuit of your VTH, or simply this, by the way, this circuit here, you can now get that current, okay, IM, okay? This is the current at the magnetizing part by having a little bit of circuit theory, right? So 384 bar 0 all over. What is this 0.5 plus J6, 0.866? This is the 1 bar 60, right? This is the ZM bar 60. But 1 bar 60 is 0.5 plus J8.66, 0.866 in rectangular form, okay? And then, okay? And then, you add the burden impedance here because on this circuit above, to get that current, 384 all over ZM plus the burden impedance. Okay, so you add all of those values there at the denominator, leaving behind ZM. Okay, how can you get E2? E2 is equal to IMZM. Why? Simply because, as I have mentioned, this is already 0. Hence, whatever your E2 here equal to EM equal to the burden, the voltage at the burden. Okay, that is IM times ZM. Okay, now what's the essence of the knee curves and as well as the these equations? It's like DC circuits. If you can still recall, you plot your DC generators E1 and E2, then get the impedance. This is also the same pattern. So as you can see, if the two equations can be solved simultaneously, with the values of E2 in terms of IM and in terms of ZM as the parameter. Plotting the curve of these values is found to intersect on the magnetizing characteristic of the curve at 600 by 5. Okay, this 600 by 5 here, our main goal. Okay, but you need to get some of the points, okay, using those two equations. Excuse me. Okay, we have these two equations here. Okay, if we apply Zm, okay, by for example 0 or infinity, what will be the value of Im? If you get the value of Im, okay, and you have the value of Zm, you can get E2. So those are the equations that we need here. If Zm is infinity, Im is 0. It means infinity, okay, that this one is open. Okay, we can explain this. Okay, this is open. Okay, if this is open because has a higher by 1 million, the current is obviously is the opposed of your ZM, Therefore, your current IM is approximately 0, right? But again, this E2 here, which is the voltage at the secondary side of the transformer, which is equal to EM, equal to EB, from what we have described a while ago, is not zero, huh? It's not zero. Why? Because this is the open circuit voltage. Although this is open, the voltage looking at this terminal point, current is zero, but the voltage at the Thevenins is equal to V open. Therefore, the answer is 384.1, not zero. Okay, now in this case, we can clear all the drawings. Then we can see it on this table. Okay. If you do it on the other parameters, okay, if you have ZM, the answer will be 3.61 for the current ZM, then E2 361, and then if you have a value of 10, okay. Now you will have a curve, no? If you have those values there, okay, create a table and get E2 versus IM. This curve, as you can see, is E2 all over IM. Secondary voltage versus the current IM. Now, for example, you already obtained this curve. This is just an example. So whatever the intersection at the 600 by 5, you can now get that current there. Sorry. You can now get E2 there versus current IM. Okay. So based from what we have no, on this example, it will be filled with these values of 17 amperes and 260 volts. Okay, if you already have that value, you can now get definitely ZM by dividing 260 by 17, and it will to this answer, okay, of 2941 ohms. Okay, definitely, if you already know that, you can now solve the other parameters of the problem, then you can now get the error, and you can now get the R, okay? But in this case, guys, you need to, okay, go back to the equation a while ago and place the 12.53 on your E Thevenins, no, instead of bar zero, simply because we make use of that as reference to get the values of IM and ZM, definitely from the meter. But when we need to get the current IM, no, you need to go back to this equation. Go back to this equation. Okay, yeah, this equation here. Okay, so what you will do is turn back the angle of 12.50. The angle there is 12.53. Okay, and then the value of your ZM, as we have computed a while ago, that is 260 all over 17, right? So if you do so, the IM here is approximately 17 bar negative 29.9 something. 97, 96. Okay, degree. So you can now get the other parameters of the system now, and then you can now get the error, and you can now get the ratio. So that's what happens on the next few slides, as you can see here. Okay, you now get the ratio correction factor of 1.47, and you get the error as 0.408. As you can see, the error is 40%, and the multiplier is 1.47. That is too much higher error. So if you want to lessen that error, you need to lessen the burden impedance, which is the 9 plus J15, I think. So lower the resistance value in order to get the turns effective ratio in a much accurate value. So that's the moral lesson of that. By designing your current transformer ratio, if you have a lower burden impedance. Okay, Now, there are times that you can also get the burden impedance, okay, by a little bit of standard class designation. Okay, so we already have the technique of getting if the ZM is linear, second dynamic. Now, how about in terms of class designation? Okay, there are some class designation already in terms of your CT. Now, the equivalent method, no, calculating the performance of a CT is depends on availability of magnetizing characteristic. And when this is not readily available, an approximate assessment of the CT performance may be made through its class designation. So it is defined by the ANSI standard and by the IEEE. Okay. Now, you have this type of the ANSI IEEE designation. Okay, it can have two integers. You have the C, you have the Okay, the first integer describes the limit on the error made by the CT when the voltage at the secondary terminals is equal to the second integer. Okay, so while the current in the transformer is 20 times its rated value, most CT secondary wine is rated as 5, which corresponds to a secondary current of 100, or the ratio is 20 times. So, ang ibig sabihin lang ng C at saka ng T, ang gagamitin natin dito, C is means in terms of class. T means transformer, means in terms of experiments. So we use the C in terms of class designation instead of the T designation. So basta ang sinasabi lang ng C is, yun nga po, the secondary transformer always 20 times the rated value, as most of the CT secondary windings are rated as 5 in terms of IEEE standard with a current of 100 ampere. Okay, we can have this example here, but later. Ay, nga pala, nakalagay na rin po dito. C means class designation. T signifies uncertainties of the transform sign. So you can get those class designations on some of the uh, uh, manuals or specification of the transformer. If you have a 10C400 type, it means it has an error of 10% with a secondary 100 amperes as explained a while ago, and which still produce 400 volts or less at the secondary terminal. Okay, for example, you consider 600 by 5 turn CT ratio. The class is 10C400. The 10C400 CT will provide 100 ampere at the secondary with no more than 10% error at the secondary side. So, we can have this analysis. The magnitude of magnetizing impedance can be computed by having 400, you divide it by the current 10%, di ba? Ang error, 0.1 times 100. So the answer is 40 ohms. That is your ZM. Okay, with a primary current of 5,000 ampere, for example, nominal secondary current will be, as we have discussed from the problem 4.2, okay, we have 5 all over 600, 600 by 5 turns ratio, so the answer is 41.66. If your maximum error is 10%, this will allow a magnetizing current of 4.16 amperes. Okay, so at this magnetizing current, it may have a secondary voltage by dividing, okay, the secondary 4.16 multiplied by Zm, which is this, right? So 4.16 times 40 ohm, the answer is 167 volts. So therefore, you can now get the error. So since the IM, since the primary current is 41.66 and the maximum burden is 167, so you can have 167 all over 41.6 minus 4.16. So where did it come from? If you can still recall, you can get I1 equal to I2 minus IM, plus IM rather. So your IM is I1 minus I2. So this is the primary current, this is the secondary current as described or solved a while ago. So it has a 4.45 uh, then impedance. So here in this case, all burdens of a smaller magnitude will produce small errors. Okay, so this is the burden impedance. You can get the ZB, right? So from there, you can already design your transformer based on classes. So what you will do if you want to have a lower value of the burden impedance, perhaps you can lower the transformation ratio in a certain way that you will yield to a lower resistive value. As we have mentioned, problem 4.1, the lower the resistive value will mean a lower correction factor. Right? Lower correction factor, the best uh, effective turns ratio. Okay. So from there, you'll already learn some things on uh, CT design or current transformer design. Okay, also from this, we can learn from CT polarity marks. Okay, polarity marking is also the same thing with you considering your mutual inductances. You can still recall. It can be added or it can be subtracted, right? Depends on the mark. The mark there is like a node, right? So tawag dun is polarity mark or node marking. Okay? Polarity markings of a transformer is means of describing the relative direction only where the current will go first and then exit. So it will go inside and then outside. So you can see the current flow. So the terminals are identified by solid marks, indicated the starting end of the two windings, meaning these are considered to be the starting point, and then trace the two windings along the transformer core so that both windings will go around the same core in the same sense. It can be counterclockwise or counterclockwise. So it means, in other words, you will have the higher polarity marking, so terminals we can designate as H1 and X2, and the secondary terminals as X1 and X2 respectively. So H1 and X1 may be assumed to have a polarity mark on them. So for example, if you have a mark on H1, it will go outside in terms of X1, then etc. So ang pinapakita lang dito is you can see the current flow. That's it. If you have a polarity and a CT, if you have a polarity mark, you can now get the current flow on that current format. Okay, we can have this example here. But anyway, our main goal here is already answered. If you have this kind of setup and you're considering the polarity marks from this example, as you can see here, so the current flow will be from this point up to this point and from this point up to this point. Okay, so the current flow is like that. And definitely this 10 ampere here is dependent on what is the result at this node. So the 10 ampere is simply equal to 5. What is the current 5 by KCL, right? Current entering equal to current leaving. You enter at this point X node, and then the leaving currents is 5 and 5. So they are the same. Okay, so that is equal to 10. You already have an idea that the current at the burden, this is burden impedance, is 10 ampere. Okay, so we can have another example by analysis only. So okay, here, so these are some examples again. So you can check it out by your own. So if you have this kind of setup here, okay, this is the current flow, and the current here is zero, no, approximately zero, not actually zero. The impedance here is very high, okay, because of the current flow. Also, the same thing with have an auxiliary transformers. So if we go here, here, and then outside. So the polarity marking is very important in getting the current flow, no, on the CTs. It's just again, no, it's like mutual inductance. Okay, you need to add the mutual inductance, or you need to subtract the mutual inductance. You can go to the mutual inductance topic. It's also the same thing here. Okay. And the rest is obviously that will be the end of our part 4 of this topic. So again, so hopefully you learn on this video, okay, and then you can apply it on your design. Okay, thank you.